Hi, my name is Rahaf Kathori, and today I'll be going over my Physics 2211 Lab 2, the motion of a falling object. The introduction. So the purpose of this lab is to compare the motion of an object dropped from rest to a computational model of the object with and without drag force. And the underlying fundamental principle that exists throughout this experiment is Newton's second law, also known as his momentum principle. I've also included the position update formulas and velocity update formulas as they are directly derived from Newton's second law. Directly below the position update formula, we can see the force of gravity on the object. Fg is equal to mg, m being the mass of our object and g being the gravitational proportionality constant 9.8. This will allow us to calculate the force of the gravity on the object. Below the velocity update formula, we can see the formula for drag. F is equal to bv squared. B is going to be our drag constant, and v refers to the velocity. Unfortunately, we can't square a vector, so we'll need to use it as a scalar, speed. Here I've included an image of my tracker model with me dropping the battery down. I've included this image so you can clearly see my system and surroundings, the system being the battery and the surroundings being everything outside of the battery. Here I've included my computational code without drag. First, we can see the ball.pos, which is the position vector, which starts off at 0, along with the ball.vel vector, which also starts off at 0, illustrating that there is no initial velocity. Below that, we can see that the b is equal to 0, showing how this is without drag. To the right, we can see how while t is less than 0.64, the while loop runs. This is because the battery is dropping for a total of 0.634 seconds. The rest of the calculations allow me to calculate the position time graph and what the formula looks like without drag. Here, I've included my computational code with drag. This is essentially the same as the computational code without drag, but now we have a b value. The b value is 0.0095 in this scenario. Everything else is the same. However, on the right, we can see how it would change with the proportionality constant for the drag being something other than 0. Here, I've included images of my velocity and time graphs comparing with drag and without drag. The one on the left is without drag, and the one with drag is the one on the right. We can see how they differ and how the velocity is not as constant for the one on the right. I will go more into this on the what if slide as we will talk about terminal velocity and the influence it has on drag. Here, we can compare the position and time graphs for the experimental position, the model position without drag force, and the model position with drag force. We can clearly see how the model position with drag force is closer to the experimental position than the model position without drag force. This makes sense as real conditions would include drag force. The model without drag force drops at a faster rate while compared to the other two. Sources of error. There's obviously going to be some error in this experiment. Some common sources of error included the rotation of the object as it'll be dropped in nonlinear motion, tracker/human error as I have a high chance of not being able to press the center of mass at every point, and dropping the object from a higher height. This makes sense as dropping the object from a higher height will result in more conformational data. So what does this mean? Which graph would predict terminal velocity? The terminal velocity occurs when the drag force and the gravity are essentially canceling out, resulting in zero acceleration. Thus, we are looking for the velocity to become constant at the very end. This is predictive of the graph on the right, as we can see the velocity to start becoming constant and the acceleration being 0. What if we threw the ball downward? If we threw the ball downward, the terminal velocity would be reached at a much quicker time, but it would still remain the same overall. This is because we're essentially adding an initial velocity, which we can see on the code on the left, causing our graph to change. The 0 would shift down to -1, but elucidating how the terminal velocity would be reached quicker, but how it would still remain the same overall. Thank you.